The previous two videos used DC for operation. Now today we're actually operating using DCC. There's a North Coast Engineering command station sitting over to the left in the picture. The reason I'm running DCC today is two of these engines have, in fact the two sitting on the sidings right now, have the older soundtracks decoders, and they'll operate only on DCC. Some of the newer engines can operate on, with decoders, can operate on DCC or DC, but these older engines actually require DCC. These block systems will work pretty much in AC, DC, or DCC because a dead block will stop an engine no matter what kind of current it's running on. Now another question you might ask is, why do you use blocks with DCC? Supposedly DCC is supposed to do away with these old-fashioned blocks. You could run this thing using a command, the cab from the DCC, to be sitting here pushing buttons all day. My question is, who wants to sit there and operate the cab continuously all day long to control trains when the trains can do it themselves by putting magnets on the bottom of them and using reed switches? This also could be fully computer controlled, which would give a more elegant operation, but the complexity of hooking up a computer would be beyond most of us. As far as these block systems, if you can follow the concept of electricity running through a wire like water running through a garden hose, you can understand the system once it's broken down into pieces. I should also mention there's a system called DCC bit switch, manufactured by Fred Hughes in Evergreen, Colorado. This uses the principle that some decoders, not all of them, but some DCC decoders when operating on DCC will de-accelerate as they encounter reverse polarity DC. There's a YouTube video on the website at DCCbitswitch.com that shows some of this stuff. Note this system, when the engines start up, like that steam engine on the siding is pulling out, they'll start up with gradual acceleration because you've got momentum is programmable into the DCC decoders. And some of them will retain this characteristic on even when operating on DC. Some will, some won't. If you had now the DCC bit switch system uses the DCC momentum for both ramp up and ramp down. With this system, you notice the engines come in and stop abruptly, so it's not quite as sophisticated using this type of system. Watching that steam engine come in the siding, you'll see when it hits the dead block, it just abruptly starts, so I have no ramp down with this system. If you were using a DCC bit switch system, you'd have both the gradual startup and the gradual slowdown. Here we just have gradual startup, but we don't have any gradual slowdown. Let's talk about some future possible changes in this system if I ever built one. Like I say, I may be the only person interested in this stuff to actually build one of these things, but I might make, the first thing is I might make a future one a bit wider. I built this one as narrow as possible. It's about 8 inches from the left to the right side here, just to make it take up the minimum amount of space on the table, but the problem is it's difficult to work on stuff in here. Plus I've got this control unit right behind the switch, so if I ever have to pull this switch off the board to work on it, it's going to be difficult to get it off. There's no room to slide it out, so it might be better to actually build this thing a bit wider and move this control unit a bit out so there's more room to work on this switch. And the other thing is on these blocks, again doing them for trying to build this unit for minimum length. The tape is actually the blocks. The reed switches are back here before the block. They don't show up well, but there's a reed switch right here by the corner of that piece of track, and there's another reed switch right here. those reed switches are what cause the turnouts to throw. Trying to keep the length to a minimum was why I put the reed switches fairly close to the block, but these actually probably should be moved back an additional 6 inches or more. You want to make sure when the magnet on the bottom of the engine or on the bottom of a car behind the engine throws a turnout, that the engine keeps going far enough to pull the magnet forward off of the reed switch. The reason for that is you don't want the engine to stop with the magnet over top of the reed switch, or if that happens, it keeps putting power continuously to the turnouts and it'll burn out the switch machine. So you want your train to pull the magnet well ahead of the reed switch after the reed switch is thrown. So for that reason, I would increase the distance. Right now I've got the magnets on the bottom of the engines are hot glued. It might be simpler just to put them on the bottom of the first car. You can stick a magnet on the bottom of an American Flyer car because they have the metal trucks, and the magnets will stick right on the bottom of the trucks. Here's the third change, and I might just eliminate the slowdown block. If you recall from previous discussions, we had these rheostats in the system for slowdown. The front rheostat slows down engines pulling out of the system when the block goes to green. The rear rheostat controls what we call the slowdown section, which extends from about. The slowdown section extends from where these pieces of tape are indicating the gap back to in front of the rear switch. There's another gap in the track back behind that caboose on that piece of green plywood where the track is mounted. That's the slowdown section. Just for simplicity, I think I might consider eliminating the slowdown sections and possibly even eliminate the startup rheostat and just use DCC. With engines readily available with decoders today, and the ability to mount decoders in these old American Flyer engines, you can use a decoder for your gradual startup, which gives it a nice gentle startup and eliminate the rheostats. Got the same system in operation here, but now we took the steam engines off the track. We've got the 3 diesels on the track. When the Erie diesel comes around the corner here and goes over this reed switch, it'll set the block to green, which will allow the train on the straight siding where the switches were lined up to it, allow that train to leave. That train sets the block to red as it leaves the siding, so the siding is now depowered again, which will trap that Erie diesel and stop it. Now when that Erie diesel went in the straight siding, it went over the reed switches in the siding and caused the turnouts to go to curve. Now when this Union Pacific diesel gets to the reed switch, it will set the block to green. The Canadian Pacific diesel on the curved siding pulls out, sets the block to red, and the Union Pacific diesel will stop. Same operation, just with 3 diesels. Again, you can see when this Canadian Pacific diesel reaches that track contact reed switch, it'll set the block to green. And the engine on the siding that's aligned with the turnouts will pull out. Here's the same system in operation. We just now have 3 steam engines. I took the diesel off the track and put the K4 on the track.